But right now, let's focus on strong titration. We're thinking here of titrating 25 milliliter of 0.1 molar HCl, and we're titrating it at 0.1 molar NaOH. And what we want to know is how is the pH changing as this titration is progressing, okay? And so what we're trying to do in this segment right here is to really to complete this table. So we just start with no NaOH, and then we're going to stop the titration at 40 milliliter of that NaOH solution. At the end of the process, we'll have this table completely filled with some values of pH. And then what we want to do is also draw something called a titration curve or a pH plot or a pH curve, okay? And we're trying to visualize how the pH is changing as we're adding more and more titrant into the flask. One of the key information you want to know here as you're calculating any kind of titration is always, one, figure out what major species are present. This is before any reaction is considered. So when you put your sodium hydroxide, when you put your HCl in there. And the second point you want to think about is what reaction occurs. Here I'm talking about a reaction that occurs to a significant extent. And so this means that the K of this reaction has to be large. There might be none. There might be only one reaction that occurs with a sizable K value, and that's the one we want to analyze. And then the last part of this is to analyze if there's a reaction, what species are present at equilibrium after the reaction. These three steps are like an ice table to some extent. You're analyzing what's at the beginning, what's happened in the middle, and then what happens at the end. But the key here is to keep in mind that we're only thinking about reactions that happen to a large extent. So we want to write the reaction only if there is a large K. So let's take a look first at 0 milliliter NaOH added. So at that point, all you have is just the 25 milliliter 0.1 molar HCl. That's the pH you're trying to calculate. And so if we think about those three questions that I just listed there, what major species is present when you have HCl around? Well, HCl is a strong acid, so the two major species that are present is H plus and Cl minus. Okay, now we have water around, but water is not going to affect the pH given those two other species that are present here. So H plus is the major determinant of pH here because there's no specific reaction that's going to occur because again there's three species that are present, H plus, water, and Cl minus. There's no reaction that's going to happen between two of these three species here. So in the end, the only thing that's going to determine pH would just be the H plus species. So then all you're dealing with is just a solution of a strong acid. So the pH of this strong acid would just be negative log of H plus concentration. Since it's a strong acid, the H plus is going to be the same as the acid concentration. So it's just negative log of 0.1. So therefore it's 1. So we can fill that out as our first number. So when we don't have anything, it's just going to be pH of 1. Okay. And I show the work right here. Now, what happens when we add 5 milliliter of NaOH? So now, in your flask, going back to this picture, you have both the HCl as well as some quantity of NaOH. Now, what's NaOH going to do for any reaction happen? Well, NaOH is going to split up to Na plus and OH minus. Okay, so what you have to think about is now you have four species. You have H plus, you have Cl minus, you have Na plus, you have OH minus. Now, I'm not discussing water right now because it's not a critical component of any of the reactions, right? So it's four species, Na plus, OH minus, Cl minus, and H plus. And what you have to think about is which two of these guys would actually react to an appreciable extent. What reaction occurs that have a large K? If you go through all of the possible combinations, the only reaction that actually happens to a large extent is this reaction right here. H plus plus OH minus goes to water. The reason is because the K of this reaction is actually 1 over Kw, right? And so it's 10 to the 14 because Kw itself is 10 to the minus 4. So this is a large K reaction. If there's a reaction, what do we have at the end, at equilibrium after a reaction? It depends on which one is the limiting reactant and which one is the excess reactant. Why do I say limiting reactant? Because this is a large K situation. The large K situation is a reaction that goes to completion So all we need to do is just figure out who's got more quantities at the beginning, and that's the species that's going to be left over at the end. So let's actually do the calculation. If I have 5 milliliter of NaOH, as we just said, the major reaction that's going to happen is just the H plus plus OH minus goes to H2O. Now we have to calculate which species has a larger quantity. For that, we're going to have to calculate the number of moles of each of the that we have. Our H plus is just whatever we have originally. It's 25 milliliter times 0.1 molar. That gives us 2.5 millimole. In this particular titration, we've added 5 milliliter NaOH. The concentration of the NaOH is also 0.1. So 0.1 times 5 is 0.5 millimole. Now we set up our ice table. Our ice table is just for this reaction. H plus plus OH minus goes to H2O. Now notice that all I care about is just the H plus and the OH minus. The H2O is liquid, doesn't factor into my K expression, so I'm not going to care about that. This is a large K reaction. That means we assume completion, right? So we started with 2.5 of the H plus, 0.5 of the OH minus. We're going to subtract both of them with 0.5. Why? Because that's our limiting reactant. So in the end, what do I have? I don't have any OH minus left. I have 2 millimoles of H plus that's left over. Now, in reality, do we have some OH minus floating around? Yes, but that's not our concern right now because the amount of H plus is overwhelmingly large compared to the amount of OH minus. So we have to calculate what is the concentration of H plus that's left in the solution. Take the 2 millimoles that we get, divided by the total volume. The total volume is 25 HCl plus the 5 milliliter of the NaOH. So that's 30 milliliters total. Calculating that would give you 0.0667 molar. This is the concentration of H plus. So the pH is just going to be the negative log of that number, which is 1.18. pH is 1.18. Now, what I want to emphasize is the concept, right? When you add the strong base to the strong acid, only reaction that matters is this H plus plus OH minus reaction. And to determine the pH, we have to figure out which reactant is left over at the end, because this is a limiting reactant situation. What I want you to do now is to go ahead and calculate the pH for addition of 50 milliliters of NaOH. The steps are pretty identical to what I just showed you, except that now you're using 15 milliliter of NaOH. Again, comparing it to the beginning stage, right? So you want to start your calculation with 2.5 millimoles of H plus, but then this now is going to be 15 milliliter instead of 5 milliliter, and you would just do your ice table and calculate pH at the end. And hopefully, if you do this correctly, you should get a pH of 1.60. Since we have the same concentration of HCl and NaOH, as long as the volume is less than 25 milliliter, the amount of H plus is always going to be in excess of the amount of OH minus. So then the pH will just depend on the H plus. So I would want you to go ahead and calculate all these other values for 20 and 24, and hopefully you'll be able to get these numbers right here. 25 is important because at that point, if I have 25 milliliters of NaOH, the amount of NaOH and the amount of HCl is going to be equal to each other. Both of these reactants are actually gone, right? So we have 0 in the end. So all we have at that point is just pure water. Base completely neutralizes the acid. The H plus and the OH minus are both equal to 10 to the minus 7 molar. That's the first important point. The pH is going to jump. Earlier we were at 2.69. Now it's going to be exactly at 7 at that point. Now the other important point about this is the equivalence point, right? How do I know? Because the amount of base is stoichiometrically equal to the amount of acid. So they're both 2.5 millimole, HCl and NaOH. And as it happens, the base and the acid here have a one-to-one stoichiometry, so that would be the equivalence point. Now what happens if I keep adding my base, if I go above the 25? If I go higher than 25, then now what I have is my base is in excess of my acid. Prior to 25, from here to here, my acid is in excess of my base. Below 25, my base is in excess of my acid. So I basically just repeat the same calculation, except that now in my ice table, the limiting reactant is now the acid. The base is going to be my excess reactant. So I'm just showing you one example of this calculation for 30 milliliter. We're going to calculate the acid, which is still 2.5 millimole. The base now is 30 milliliter with 0.1 molar, so that gives me 3 millimoles. I put those numbers in my ice table, but now notice that This is the limiting reactant, the acid, so minus 2.5 for both. I have some base left over, half a millimole. I can calculate the concentration of that base. It's half divided by the total volume. The total volume is the acid, 25 milliliter, plus the base I'm adding, which is 30. So it's 55 milliliter total. Calculating this gives me a concentration of 0.00909. That's my hydroxide concentration. Again, no longer H plus because all the H plus is neutralized by the OH minus. So what's the pH? Since I have an OH minus, I have to use the 14 minus PO8 calculation. It's just calculating a strong base solution. And so what I have is a pH of 11.96. So that should be what you get when you do the calculation for 30 milliliters NaOH added. What I want you to do is complete the other two values there for 26 and for 40, and you should find 11.29 for 26 and 12.36 for 40. One of the things I want to highlight before we do our plot is how the pH is very low before the equivalence point. This point right here is 1 milliliter before the equivalence point. And you notice how low that pH is. So there's a huge jump going from 24 to 25 in terms of the pH value, 2.69 all the way to 7. The same jump is observed when you go from the equivalence point to the next base point, which is right here, right? Notice that it goes from 7 all the way to 11.29. So a big jump there. So the plot that we're going to do for the titration plot for a strong titration would look something like this. You're going to put your pH on the y-axis and the volume of NaOH on your x-axis, and this should be in milliliter because the NaOH is titrant, is the thing that you're adding. Right? And what we expect to see is we're going to get very slow increase in pH. So it goes from 1 to 2.69 when the volume goes from 0 to 24. So let's say it's 2.69 right here. So it goes from 1 to 2.69. All of a sudden at 25, which is the point right next to 24, the pH is now 7. And then all of a sudden at 26, which is the point right next to it, it goes all the way to 11.29. So it's all the way up here. So you want to plot this to show that change in the pH value. So I'm going to use a different color here just so that everybody can see that that portion of it is really steep. Okay. And then after you reach that next point though, the pH changes only slightly, 11.29 to 12.36 as you're going through 40 liters in volume. So when you get to 40, the pH has gone up, but not gone up by a whole lot. So again, you get this gradual increase in pH. So that would be what a strong titration or pH curve looks like. I actually took the data that we had calculated and just plotted them in Excel, and this is the result of it. And you can see again how steep that changes between the three different points there, right before equivalence, at equivalence, and right after equivalence. But then prior to those points, change is pretty gradual, and then after it, it's also very gradual. So there's really only three different parts of a strong titration. The part right here is our strong acid region, right? Where the strong acid is in excess of the base. And then we have this top part right here, which is our strong base region. At that point, the strong base dominates. And then we have the equivalence point, which is when it's completely neutral. So the equivalence point is pH equals 7. And that's always true for a strong titration, whether you're doing strong base titrated with strong acid or strong acid titrated with a strong base. So these three conclusions are written here and they apply to all strong titrations.